Hello and welcome. In this video, we are going to prove the fundamental theorem of algebra using complex analysis. So the theorem states that every non-constant polynomial over C has at least one root inside C. That is, the C as a field is algebraically closed. So we are going to consider first polynomial P of Z over C. So first thing to notice here is that we can always make it monic since C is a field. So P of Z is monic. So we're going to prove it using contradiction. So suppose that what we want to prove, that P of Z has at least one root in C. That is, P of Z is 0 for some Z belongs to C. So suppose that P of Z is not equal to 0 for all Z belongs to C. And then we want to arrive at contradiction. So we're going to use the complex analysis here. So we're going to use in particular the Liouville's theorem, which states that entire and bounded function is a constant. So we're going to consider a new function f of z, which is the reciprocal of p of z. So this is well defined because we consider that p of z is not equal to 0. So this is well defined for all z belongs to C. And notice that this is p of z is a polynomial function, so it is differentiable for all C. And it is just a reciprocal of that, so the composition is again differentiable. So f of z, f is differentiable for all z belongs to C. So we get that f of z, that is f is entire function. So now we have considered this reciprocal because we want to show that f is bounded, and if we shown that f is bounded, then we will get f is entire and bounded and f is constant. So it is not possible since p of z is non-constant polynomial. So now take the bound for f of z. So 1 upon p of z, that is 1 upon I will take z just to in common, so I will get these terms right here, n minus 1 z all the way up to a naught z raised to n. So now notice that this term right here is converges to 1 as mod z tends to infinity. We can prove it easily using triangle inequality for showing upper bound, and for giving lower bound we can use reverse triangle inequality and then squeeze theorem to prove that this limit as mod z tends to infinity is 1. So we'll get that this f of z converges to mod 1 upon z raised to n, and as z tends to infinity, this thing will go to 0. So what we got is mod f of z is tends to 0. So what that does mean, for all epsilon greater than 0, there exists some r, some radius r, such that for all z greater than r, f of z, mod f of z is less than epsilon. So we got the bound for f of z, mod f of z for all z greater than r. So for z less than equal to r, so r is basically some radius. So we got f of z is less than mod f of z is bounded outside this region. So this z less than equal to r is a closed region, right? So we know that there is theorem in real analysis that if on closed and continuous interval, it is there exists bounds, so it is bounded. So there is such a same theorem in complex analysis, that if the region is bounded and function is continuous over that region, if the region is closed and function is continuous over that region, then we got the bound. We will always get a bound for the function over that region. So there exists some m such that f of z is less than m for all z inside, for all z less than equal to r. So we have basically shown that f of z is bounded inside and outside this closed disc. So that is f of z is bounded for all z belongs to C. So we have shown that f is entire and bounded function. Then by Liouville's theorem, f is constant. So, but that is not possible since f is reciprocal of p of z, which is non-constant polynomial. So this is contradiction, and hence our our claim is false, and therefore p of there exists some z belongs to C. There exists some z belongs to C such that p of z equal to 0. So that's the theorem. Thanks for watching. In the next video we are going to prove the fundamental theorem of algebra using Galois theory, which is more independent proof.